we defined covariance last time. Let's spend just a little bit of time talking about random vectors. In the case of a random vector with n elements, we can talk about the covariance between entries in this vector. And we summarize the covariances of the individual xi, xj terms as a matrix that we call the autocovariance matrix of the random vector. So that kxx has entries sigma 1 squared, sigma x2 squared, the variances, in other words, as the diagonal terms. And the off-diagonal terms are the covariances of the respective components. This is the covariance of x1, x2, and this is the covariance of x1, xn. Here we have the covariance of xn, x1, which is of course the same thing as the covariance of x1, xn. Therefore, this matrix, by its definition, is symmetric. So the autocovariance matrix is a symmetric matrix. The diagonal entries are always positive, and it is a positive semi-definite matrix. Now, in the case that the autocovariance matrix is a diagonal matrix, this means that the individual components of the random vector are all uncorrelated. In the case of the random variables being independent, they're automatically uncorrelated. Therefore, the autocovariance matrix also reduces to a diagonal matrix. Now, let's see an example of uncorrelated random variables and computing expectation and variance. Very simple example. Suppose a random variable x is defined as the sum of random variables b1 through bn, and each of these bi's are Bernoulli with parameter p, and they're uncorrelated. In that case, the expectation of x is simply the sum of the expectations. This is always true. It doesn't require any uncorrelatedness, obviously, because expectation is a linear operation. And the expectation of the sum is np. The variance of the sum, because of the uncorrelatedness, is the sum of the variances. And this is n times the variance of one of them, because they have the same distribution. The variance of a Bernoulli random variable is p times 1 minus p. So np1 minus p. Incidentally, if y was given to be a binomial random variable with parameters n and p, we could always represent y as the sum of n IID Bernoulli random variables, independent and identically distributed Bernoulli random variables. In that case, all of the above would be valid because of the independence, they're uncorrelated as well. So for a binomial random variable, the expectation is np, and the variance is np1 minus p by this computation.